Hi everyone, and welcome to the third installment of AIME Improvement. This week's TJAIME topic is geometry, basic geometry. And if you look in the handout, there's a ton of different formulas and stuff that uh, I really can't cover in one video. So I'm just going to do two problems and uh, give you guys some insight as to how people think when they do geometry problems. So this first problem is from ARML. It says hexagon ABCDEF is inscribed in circle O with AB equals CD equals EF, which is double each of BC, ED, and AF. So here it's kind of alternating, say a length X and then length 2X, so double that, and then X and then 2X, X and then 2X. So just alternating. And then if we have AD equals 8, we're given that, we want to compute the perimeter. So if we add it all up, we get 9X. That's what we want. So if you look at this, we don't really know much about how to deal with random hexagons. Like we know how to deal with regular hexagons, but random hexagons, not so much. Luckily, we know a couple things. First of all, we know that this hexagon is cyclic. Second of all, we know the lengths. Well, we don't know the actual lengths, but like we know their relative lengths and we know a particular diagonal's length. So this should be enough for us to do this. So taking a look here, you might be trying different things. You might be trying maybe like dropping perpendiculars and doing computations like that. But I think the cleanest way to do this is with symmetry. So if we draw these radii, then you notice that this arc is composed of an arc with a chord x, an arc with a chord 2x. This arc is composed of an arc with a chord x, an arc with a chord 2x, and so is this one. And so each of these are actually the same angle measure, right? Just by symmetry. And so all of these are 120 degrees. And so what this actually gives us is if we draw this BE, then this angle is half of FOB, so it's 60 degrees. And now we have a cyclic quadrilateral AFEB. We know FEB is 60 degrees. So we actually know that this is 120 degrees. And so at this point, something that you could say is, for example, if we drop these perpendiculars now, let me redraw this, then what we actually get is 2x 60 degrees here and x and 2x. So if we draw perpendiculars, then since these two are parallel because it's an isosceles trapezoid, it's in a circle, then this length is x. And from 30, 60, 90 properties, this length is x and this length is x. So 3x is actually equal to 8. Why? Because BE equals AD equals 8. So now we know that 9x equals 24. So this is actually a really fast problem if you just mainly take advantage of the symmetry. After you take advantage of this, there are different things you could use. You could use like law of cosines up here with this 120 degrees. But really the fastest way is to just look at this 60-degree angle and be like, hey, we can work with that and go from there. So the second problem is a bit more involved, mainly computationally. So it says circle C, I've already drawn this diagram by the way, I hope you guys don't mind. Circle C has radius 2, let's underline that because I didn't mark it in the diagram, and it has diameter AB. So the center of C is somewhere here. So this is the center, this is, say, circle. Circle D is internally tangent to C at A. And here I've drawn that. D is internally tangent to C at A. And because of that, the center of D is actually on AC. And so we also have E as internally tangent to C, externally tangent to D, and tangent to AB. I've drawn that. So we have a lot of tangents. If we draw this inner tangency point here and call it like X, draw this here, call it like Y, then we actually have that XYC are collinear, or not XYC, if this is E, we have XED are collinear and EYC are collinear because properties of tangents. This is internally tangent to this circle here. This is externally tangent to this circle here. That's all it is. And we also have that the radius of D is 3 times the radius of E. So if we call the radius of E R and draw these in, then we have the radius of D is 3R, draw these in. And so we have, uh, let's say this from the center, right? This whole length is 2 because radius of C is 2. And so this is 2 minus 3R. So at this point, you might be trying different things like law of cosines, law of sines, whatever. But I think the fastest way from here is to say, first of all, CE is 2 minus R because this is radius 2 and we're taking out this radius R. And at this point, we want to drop this perpendicular. Where does that come from? Well, if we think about what we used so far, we've used E as tangent to D, we've used E as tangent to C, we've used D as tangent to C, but we have not used that E as tangent to AB yet. And so, like, that's basically the inspiration. Whatever we're given, we know we're going to want to use, and so we draw that in. Plus, in general, if you have tangencies, you want to draw them in. Like I've drawn in these tangency points, but like that's really motivated because they exist. You know that they exist, so you draw them in. So that's like what a lot of geometry is, getting used to, okay, we know these facts, let's draw it in, and then as you do more and more problems, you'll kind of like recognize patterns and configurations and diagrams, and you'll know what to draw in from that point on. You'll know what's useful. So at this point, we have this right triangle here with a little right triangle inside, and we know a lot of lengths. So I'm just going to pull it out so it's not so messy. So it's something like this. Because this is tangent to a line, then this is 90 degrees. And we also have that this is 4R, this is R, this is 2 minus R, this is 2 minus 3R, and we don't know this length. So if we call this length X, then we actually have two equalities. So we have X squared equals 2 minus R squared from this right triangle right here, this little one, minus R squared. So X equals square root of 4 minus 4R. Now from this big right triangle, we have that X plus 2 minus 3R all squared equals 4R all squared minus R squared. So X plus 2 minus 3R equals, doing this out and square rooting, we get square root of 15 times R. So X equals square root of 15R minus 2 plus 3R. So now we can set these two equal. So we have X equals both square root of 4 minus 4R. So let's just write it as 2 square root of 1 minus R. And it also equals square root of 15R, no, square root of 15 times R minus 2 plus 3R. And at this point, what we really want is the radius of D, so 3R. So at this point, we have everything we need. Let's solve. So we have these square roots. Obviously, we need to clear them out. And so I like to move the not square rooted stuff to the one side and the square rooted stuff to the other side. So we have 2 minus 3R equals square root of 15 times R minus 2 square root of 1 minus R. Squaring both sides, 4 minus 12R plus 9R squared equals 15R squared plus 4 minus 4R minus 4 square root of 15 times 1 minus R times R. You can verify this, but essentially I just square both sides. So now I would like to keep the R squareds with positive coefficient. So let's move the square root on this side and everything else on the right. So we have 6R squared plus 16R. Is that plus 16R? Right, plus, oh no, plus 8R, because this is minus 4R. And then the 4's cancel, and this is all equal to 4 square root of 15 times 1 minus R, and then times R. And at this point, we can cancel out an R, which is really nice because R is not 0. And we can say, okay, so cancel out these, and we get 3r plus 4 on this side. And now we square again. So 4 times 15 times 1 minus r is equal to 9r squared plus 24r plus 16. Again, just from squaring both sides. And now we've run out of square roots, which is good. So moving everything to the right, we have 0 equals 9r squared plus 84r minus 44. And quadratic formula. So we have r equals minus 84 plus or minus, but if we had minus, then we would have a negative minus something, a positive, and then all over 2 times 9, 18, which is positive. So the end result would be negative, and since lengths can't be negative, then we know that this has to be a plus. So yeah, plus square root of 84 squared plus 4 times 9 times 44, and then everything is over 2 times 9 is 18. So we know that 3r is going to be this over 6. So at this point, we don't want to compute all this out, so let's pull out what we can. Let's pull out a 4 first. So these cancel, and this becomes 11. This becomes 21 squared. And now we have a 9 here, something multiple of 3 all squared. So pull out a 3. And we have 7 squared plus, pull out this 9, 7 squared plus 11. And so this is equal to minus 84 plus 12 square root of 49 plus 11 is 60 all over 6 equals minus 14 plus square root of 240 if you do this out. And we know that this is equal to square root of m minus n, so m plus n equals 254. So really what's important here is drawing in these tangents and then using all the relations you have to reduce it down to just algebra. So this is what a lot of length computation problems are going to be like. Take the relations you have, think about, okay, what can I do with this, and try to turn it into just an equation. So that's all from me today. Thanks for watching.